Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over analysis of rational functions. We're going to be finding discontinuities, asymptotes, intercepts, and we'll graph the resulting function. Alright, the instructions are as follows. For the given rational function, we are to find the discontinuities, the asymptotes, intercepts, then a graph. Okay? Alright, so let's say we have the following rational function, f of x equals 2x plus 1 times 3x minus 1. This entire numerator quadratic divided by 3x minus 1 times x plus 2. Alright, we're going to start out by looking for the discontinuities. Okay? The discontinuities of a rational function is also known as the poles of that function. Okay? Now, how do you find the discontinuities? You simply find the zeros of the denominator. Okay, so finding the zeros of the denominator will determine the discontinuities or poles of the function. So if you take a look at the function that we have right here, the denominator function is 3x minus 1 times x plus 2. Okay, so we're just going to extract the denominator as it is and set it equal to 0. Now, using the zero product property, we set both factors to 0 and then we solve. To solve this, we add 1 and divide by 3, so we have 3x equals 1. Divide by 3, we have x equals 1 over 3. Okay, so that's the first discontinuity. And then the second discontinuity, you simply subtract 2 from both sides. You have x equals negative 2. Okay, so our discontinuities are the set containing the values negative 2 and 1/3. Alright, now we can break up our discontinuities further into the removable discontinuity and the infinite discontinuity. Okay, so what are the removable discontinuities? The removable discontinuities, also known as the wholes of the rational function, can be found by taking the zeros of the cancellable denominator factors. Okay, so we're looking for the zeros of the cancellable denominator factors. Okay, so we look at the original polynomial function and we'll ask ourselves which denominator factor can be cancelled with another identical factor in the numerator. If you take a look at this, we can clearly see that 3x minus 1 represents that cancelable denominator factor in this scenario. Okay, so since that's the cancelable denominator factor, we're going to extract that particular factor, which is 3x minus 1, and we're going to find the zero of this factor. Okay, so 3x minus 1 equals 0, Add 1 to both sides. And then when you divide by 3, you have an x value of 1/3. Okay? So this right here is your removable discontinuity, also known as the whole of the rational function under consideration. Alright, some discontinuities are removable, some are not. The ones that stay or cannot be filled up with a point, for rational functions, those are known as the infinite discontinuities. Okay, so your infinite discontinuity, these can be found by finding the zeros of the uncancelled. Okay, for a removable discontinuity, we're looking for the ones that can be cancelled. For the infinite discontinuity, we're looking for the zeros of the ones that cannot be cancelled, or the uncancelable denominator factors. Okay, so what we're going to do is revisit the original polynomial function, and we'll ask ourselves which denominator factor cannot be cancelled or does not have an identical factor with any component in the numerator. This is when the rational function is expressed in its factored state. We can clearly see that x plus 2 cannot be cancelled because there are no x plus 2 quantities in the numerator of this rational function. Okay, so we'll simply extract that denominator factor that cannot be cancelled, set it equal to 0 and find a 0. In this case it is -2. Okay, this is the infinite discontinuity of the rational function under consideration. Next, let's go into our asymptotes. We're going to start off by looking for our vertical asymptotes. Okay, our vertical asymptotes can be found by simply looking at your infinite discontinuities. Okay, so these are the same as the infinite discontinuities. Okay, the nice thing about this problem is that we have already found the infinite discontinuity as x equals 2, so our vertical asymptote is simply x equals -2, not 2. Sorry, so x equals -2 is our vertical asymptote. Alright, moving along, let's find the next asymptote, the horizontal asymptote for this rational function. For the horizontal asymptote, we're going to be looking at the weight of the degrees. Okay, the degree weights, how do they compare with one another? Okay, so what do I mean by degree weights? If it's top heavy, indicates that the degree of the numerator is greater than the degree of the denominator. In this case, there are no horizontal asymptotes. There could be slant asymptotes, but for horizontal asymptotes, there are none if you have a top-heavy scenario. Okay? What if the degree of the numerator and the denominator are identical? In that case, we have equal weights. In this case, you just simply divide the leading coefficients, and that will give you the horizontal asymptote. Alright, so it's either top heavy equal weight or bottom heavy, where the denominator's degree is higher than that of the top. In that case, we have y equals 0 as our horizontal asymptote. Okay, so let's go ahead and rewrite the function that we're working with here. Let's change the color. A function is f of x equals 2x plus 1 times 3x minus 1 divided by 3x minus 1 times x plus 2. Now what I need to do is I need to determine the degree of the numerator and the degree of the denominator. Okay? To figure that out, I simply need to determine what the leading terms are for the numerator and the denominator. Okay? So the leading terms are as follows. Now the question is, do I have to expand the entire thing to find out what the leading terms are? The answer is no. All you do is take the terms with the highest degree in each factor and multiply them with each other. So in 2x plus 1, this is the term with a higher degree. So you multiply 2x by 3x. That yields 6x squared. That's the leading term of the numerator. Follow the same procedure for the denominator. 3x has a bigger degree in this factor. X has a bigger degree in this factor. Multiply them by each other, and we get 3x squared. Okay, in this particular scenario, we have what? Top heavy, bottom heavy, or equal weight. The degree of the numerator is equal to the degree of the denominator, which is equal to 2. So what does that mean? We have equal weights. Alright? When you have equal weights, you simply divide the leading coefficients, or the leading terms, you get the same thing. 6 divided by 3 is equal, 6 divided by 3 is equal to 2. So we have 6 over 3, which is equal to 2. So our horizontal asymptote, remember, is the y line, is y equals 2. Okay? So that is our horizontal asymptote. Alright, let's go ahead and find the intercepts. Alright, so for our intercepts, we're going to be looking for our x and y intercepts. Okay, so let's start with our y-intercept. To find our y-intercept, we're simply going to do what? We're going to set x to 0. Okay, and solve. Set x to 0 and solve. That will be our y-intercept. Alright, so we know f of x is equal to y, so we're just going to write y. So we write the original function using y equals 2x plus 1 times 3x minus 1 divided by 3x minus 1 times x plus 2. Okay, so to find the y-intercept, we are setting x to 0, so basically what we're doing is evaluating the function at x equals 0. So we're going to have 2 times 0 plus 1 times 3 times 0 minus 1 divided by 3 times 0 minus 1 times 0 plus 2. When we simplify this, we'll get 1 times negative 1. That divided by negative 1 times 2. Okay? So y-intercept is going to be negative 1 over negative 2, which reduces to 1/2. Alright, so y-intercept is equal to 1/2. We just have one, well, we have one y-intercept here. Okay, now let's take a look at our x-intercept. For our x-intercept, what do you think we are going to do? For the y-intercept, we set x to 0. So for our y-intercept, we're going to set y's to 0. Okay? The faster way to do this will be to just set your numerator to 0, because when you cross multiply, your denominator will disappear. So just set numerator to 0 is equivalent to setting y to 0. Okay, that's the fastest way to do it. So when we set the numerator to 0, we have 2x plus 1 times 3. Well, actually, we have to reduce first. So when we reduce, we cancel out the 3x minus 1. So this 3x minus 1 and that 3x minus 1 is gone. And we have 2x plus 1 equal to 0. Okay, so that's a numerator factor that's left after reduction. And we'll go ahead and solve this. You subtract 1 from both sides, you have 2x equals negative 1. And then divide both sides by 2. That gives us our x-intercept of negative 1/2. Okay, so we have one x-intercept, and we have our y-intercept of positive 1/2. Okay, now let's put everything together. Let's sketch the graph of our function, and then we'll check our work by using the graphing utility. Okay. Alright, so we have our y-axis and our x-axis. Let's start by looking at what our vertical asymptote is. It's a guiding line. Our vertical and horizontal asymptote. A vertical asymptote is -2. Horizontal asymptote is y equals 2. Okay, so let's go ahead and graph those. So let's call this -1, -2 for my vertical asymptote, 1, 2 for my horizontal asymptote. Okay. Alright, so I'm going to make my vertical asymptote blue, like that. And then let's make the horizontal asymptote red, like that. Okay, so the nice thing about drawing your asymptotes first is it's easier for you to insert your curve. We also have an x-intercept of negative 1/2. So that's going to be right here. And then we have, do we have a y-intercept here? Yes, we do. A y-intercept of positive 1/2. So that basically helps us to see what the graph is going to look like. Okay, so let's go ahead and insert the curve. It's a rational function. So in this case, since the degree is going to be 1 in the numerator, and denominator, then we're going to have something that looks like a hyperbola. Okay, so just connect the dots like that. And then we have an identical behavior happening here. Okay, so let's go ahead and graph that. So to get to this point, we go 1, 2, 3, 4, 1, 2, 3. So the same thing here, 1, 2, 3, 4, 1, 2, 3. Put a point here. And then for the other one, to get to this point, you just go 1, 2, 3, 4, 1, 2, 3. So 1, 2, 3, 4, 1, 2, 3, right here. Okay, so just draw something that looks identical to what we drew here. Now remember, your asymptotes basically represent lines that the curve gets infinitely close to but doesn't touch or cross as you tend in the direction of that line towards infinity. Okay, so you have the line going, it's going to go closer and closer to this asymptote, but it's not going to touch or cross it as you head upwards. Okay, so this is what our graph looks like. We also have a hole somewhere, or our removable discontinuity. What is that? Our removable discontinuity is that x equals 1/3. Okay, so how do we show that? You simply put a hole where 1/3 is. 0.5 is somewhere here. 1/3 is smaller than that, so somewhere to the left of 1/2. we have a hole there. Let's draw that again. It's basically an open circle. That's how to depict a removable discontinuity. Okay, let's label what we have. This is a horizontal asymptote. Just to give the names of visual representation, horizontal asymptote is the line y equals 2, and right here we have the vertical asymptote. Vertical asymptote, and it's the vertical line with the equation x equals -2. Okay, and here we have our y-intercept of 1/2, and this point represents our x-intercept of -1/2, and this open point right here represents our hole or removable discontinuity. Removable discontinuity which has a value of x equals +1/3. Okay, so this is basically what the rational function looks like. Thanks so much for taking the time to watch this presentation. I really appreciate it. If you found the contents of this tutorial helpful in your studies of rational functions, do give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions or comments about what we covered in this tutorial, just place it in the comments section below, and we'll be more than glad to support you. Don't forget to subscribe to our channel for updates to other math tutorials such as this. More content can be found on mathgotserved.com. Thanks again for watching, and have a wonderful day. Goodbye.